slideshow's set. All right. And before I get going too much on this, let me just ask a couple of questions. I hate that we lost the full hour plus a little bit. Do you want to try to make this up? The only times I have to do it would be Monday, Wednesday afternoons, anytime after 2 o'clock, to make up the hour class we missed. No, okay, well, y'all are kind to me, okay. So, we'll just try to move as quickly as we can through what we've got left. So, where do we stand? And I must say, this is a great class. It's the first class I think I've ever had, science class, that everyone turned in the lab on the day and everyone did the test on the day, and they're all graded. In fact, I can return them to you now. I hadn't thought I should have been doing that while we're waiting for the system to come up. What's that? You didn't want me to dismiss it? Is that what you said? Okay. Y'all are fine. Okay. I ate lunch in the doctor's office. What lunch I had. Pius not here. Cassidy.
I'm sure we all appreciate Christy for trying.
Pardon me?
We all appreciate her for trying.
You want to know this?
I was planning to eat most of it on the way home, and Christy, I'm sorry, I got you. Okay, Chris. Okay. Guy's not here. Kayla, not here. Adam, not here. Justin. Warren, not here. Okay. I tell you, that's the earliest I've ever been able to get back to the lab. Because most of the time there's at least one person who hasn't turned it in on time, and I have to wait for usually it's more than one. So here's the test. First time I've given, I think, testing. Everybody was there ready to take it. Good. Team. Chris. Not here. Kayla's not here. Adam not here. Justin. Warren not here. All right. More people aren't here today. I hate for them to miss this much class. Even though I guess if there was a day they had to miss, this would be probably preferable than a full class. But okay. So, any questions on anything we've covered so far? The lab I returned, the test I returned, or what we've covered so far in chapter 15? All right. Closest planet to the sun, what? Mercury. Also, how does Mercury fit in the size of the planets? Smallest planet. Now, that Pluto is not considered a planet. Mercury is the smallest planet. Okay, what can you tell me about Venus? Venus is the closest planet to Earth in many ways. It's the closest physically to Earth. It's the closest to Earth in size. It's that's where about everything ends, okay? Its orbital distance, remember, Mercury was about, with the the Sun to Earth being here, Mercury was a little over a third of the way. Venus is almost 3/4 of the way. Okay? So from the Sun to the Venus is about 3/4 of the way from the Sun to Earth. Okay, 7/10. Often called the morning and evening star, though certainly it isn't a star. After the Sun and after the Moon, Venus would be the brightest thing in the sky if it's visible. It's the first bright thing you'll see out there after the sun sets, and before the sun rises, it's the last one to disappear if it's visible. Okay? Now, it also exhibits phases. I've never seen this with my naked eye, so you would have to be looking through a good pair of binoculars or a telescope, but then you would definitely see the phases of Venus. In other words, sometimes you'll see a full Venus, sometimes you'll see a half Venus, a gibbous Venus, or a crescent Venus, okay? So it will exhibit phases just like the moon does. Okay, we'll talk about that more in the next chapter. Here is the strangest thing about Venus. Its rotational motion is opposite to the orbital motion, okay? If it's orbiting around the sun like this, it's rotating like this, backwards. It's the only planet that does that, okay? And what's even worse, remember Mercury's day was about 2/3 the length, the year was about 2/3 the length of a day, so it had about 1.5 days every time around. Venus is even worse. Its day, one spin, is actually longer than its year, which is one revolution. So it's spinning very slowly and spinning backwards. And the Venusian, okay. So in other words, if you're on Venus, which you'll never be, and you don't want to be, even though women are supposed to be from Venus, you don't want to be from there. It's a good place to be from, I'll put it that way. Okay, but you would see the sun rise in the west and set in the east because it spins backwards. Okay? Now, being the closest planet to us, not the closest object, the moon's the closest object, but being the closest planet to us, we have sent numerous probes to Venus. Okay? Now, when I say we, I mean humankind. For some reason, the Soviets jumped all over Venus and were sending things there, so we decided to go to Mars. Okay? We just wouldn't do the same thing Soviets did, which may be good. We learned things about both of them. All right, and here is why you wouldn't want to be there or be from there. The atmosphere is mostly carbon dioxide. And it's the only planet I think you can say that about. Okay? Now, what do we call carbon dioxide? If there's too much carbon dioxide in our atmosphere, what do we call it? Okay? It could be considered pollution. Usually that's the smoky, dirty stuff. The carbon dioxide is clear. But what does extra carbon dioxide cause us to do? Second? Heating. Yes, it's called a greenhouse gas. It holds heat. It holds the temperature. That's one reason they think that temperatures are rising. My wife showed me a app or something she found the other day, and it shows from 1850 to present temperatures, and sure they fluctuate, but the blues being cold and the reds being hot, very blue down here, with sometimes it getting less blue and stuff like this, and very red up here with no blue at all. They have been warming. You can't say they haven't, okay? They have been warming since 1850. Now, before that, they probably, I don't know. But since 1850, we've been doing more industrialization. We've been burning more fossil fuels. Has to be a correlation there, okay? So it's a greenhouse gas, meaning it traps heat. And in addition to being carbon dioxide, extraordinarily high temperatures, and high pressure. Okay? A few things they don't mention in the atmosphere. It has a fair amount of sulfur dioxide, which combined with a little bit of moisture makes it sulfuric acid, which is not a very pleasant thing. So it has probably the densest atmosphere. gives it the greatest pressure. CO2 is closer to the sun than we are. The atmosphere traps heat way worse than we do, and it's just hot. It is incredibly hot. Okay? In fact, there's other things in the atmosphere that would be liquid if that was on the Earth. It might even be solid if it was on the Earth. It's so hot, there's a lot of trace stuff in the atmosphere. On average, now this is, okay, remember, Mercury's here about a third of the way from the sun to the Earth. Venus is out here 7/10 as far, so it's over twice as far as it is from sun to Mercury as it is sun to Venus. Okay? And yet, on average, Venus is hotter than Mercury, even though it's more than twice as far away from the sun as Mercury. Any guesses why? That atmosphere traps the heat, really traps the heat. And remember we said, and this is the other thing, on average, Mercury, it spins kind of slowly, about once every 2 months, 3 months, okay? It spins. So the side facing the sun is hotter than Jupiter for sure. But the side away from the sun, because it has, how much atmosphere does Mercury have? A big fat zero, no atmosphere. So therefore there's nothing to trap the heat. So the side of Mercury away from the sun is frigidly cold, okay? So the average temperature on Venus, since it has this huge blanket all around it, the thickest, densest, most highly carbon dioxide atmosphere of all the planets, it traps heat like crazy. And Venus turns real slowly too, but you can't tell. Day or night, whether you're facing the sun or away from the sun, it's hot. It's incredibly, incredibly hot. Okay? Now, the surface of Venus is mostly flat. Would you expect to have many craters on Venus? Why not? That thick atmosphere, anything trying to come through it, it's going to burn up in the atmosphere. The atmosphere is thick, dense, and hot. If anything made it through, it's going to be pretty major. Now, I believe one of the times we went to the planetarium at Sanford, the guy there said, if I'm not mistaken, they think that perhaps Venus, early in its history, way, way, way a long time ago, maybe 10, 12 billion years ago, early in the sun formation, when there was a lot of space junk flying around out there from the formation of the sun, that it may have been really crashed into a big asteroid or comet or something like that, and that may have been what knocked it and made it start turning backwards. Okay? Now that's speculation. I don't know if they have any way to tell for sure, but that's a speculation. Now we haven't gotten to Earth yet, but there is some and how many moons does Mercury have? Zero. How many moons does Venus have? Zero. Okay? How many moons does Earth have? One and only one moon. Okay? And here's a speculation again about our moon. They think there's a fair amount of evidence that may have been broken off from the Earth at some huge collision very early in our formation process, and it may be part of us. One thing that supports that, we never see the backside of the moon. It spins one time for every revolution around the Earth. We only see one face of the moon. It turns one time on a revolution, but it revolves that one time. We only see that side. So that sort of makes sense. It was once part of the Earth, and it's continued to face us that way. Okay? The composition, other things lend to that theory as well. So evidently there was a lot of traffic violations, and run-ins and things like this early in our solar system formation. Venus may have gotten hit, we may have gotten hit. Okay? So Venus surface is mostly flat but varied. Anyone want to make a guess about what could be some of the variation? Mountains, okay? Now, we'll get to in several chapters from now why mountains formed on the Earth, and there's like 2 or 3 reasons, 3 at least. If anyone knows those, what would you speculate why there might be mountains on Venus? Did I mention its temperature?
Yeah, you said it's hot.
Say again?
I know it's hot.
Okay, it's hot, and one of the things that contributes probably to that too, and maybe the carbon dioxide release, is a lot of volcanic activity. Just like the Earth has volcanic activity, the Moon at one time had some, they think. Probably other planets have too, but Venus is so much like the Earth, so similar in many ways, it probably has the same, and I'll get to this chapter later, plate tectonics. So it probably has faulted and folded mountains and also possibly volcanic mountains. Okay? Now, this shows the numerous probes. Okay? And as I said, the USSR, back when it was the USSR, Union of Soviet Republics, what we call Russia. Huh? I wish. It's in the book, if you got the book. But no, don't worry about this. You don't need to memorize or know anything about it. But you'll see that they are by far the most frequent visitor to Venus. Now, a lot of these were flybys. They just went by the planet, took pictures, and got a T-shirt. No, I'm sorry. That kind of stuff. And if you look at the names of some of these, here's one from the U.S. named Mariner. Here's one named Mariner. Here's one named Mariner. Guess where they were really heading? Mars! But they just happened to fly by Venus on the way and take pictures and that kind of stuff. They started off that the Soviet Union's Venera 3, that's Venus's 3, actually crashed on Venus. That doesn't sound like it was on purpose, okay? Venera 4 impacted Venus, which may be another way of saying it crashed, but maybe they meant that, and these two did too. But then they actually landed on Venus a couple of times. And again, mariners showed up, and we just took advantage and took pictures and things like that. The Soviet Union finally, in '75, got a couple of landers orbiters. Okay, landers meaning actually went to the surface, orbiters stayed in orbit around. So, we finally got an orbital study of Venus here, and here is. She thought I was going to be at the doctor's office really late, okay? Lauren, okay, good. And by the way, before you go today, I got your lab and test I can return to you. As I was telling the others, this is the first ever science class I've had that everybody turned in the labs on the first day and the test on the first day. So I can return them to you on the next day. I hope it continues. Okay? So you can do that. Yeah, you don't have to, nothing on here is memorizable or anything else. Don't worry about it. Here is the pioneers. They actually did orbital studies of Venus. That wasn't the only place they were going, but they stayed and went around several times. Okay? And then finally, orbital radar mapper, and Galileo took more measurements and photos. Our technology kept getting better and better and better. But you see, for the first, how many years? Almost 30 years, it was all USSR and US. In some of the most recent times, the European Union has gotten involved, Japan has been involved some, but it's mostly been, and now it's Russia, not USSR, but they probably have still sent some things up. Okay. Here is one of those pictures. One of the landers actually took on its way down. They've had to probably enhance some stuff, but this looks like a lava flow here, and more than likely it is, so that indicates volcanic activity. This probably is a volcano here, so when they say mostly flat, no, there's plenty of mountains, plenty of terrain interruptions there, okay? Because there's a lot going on Venus. Not a hospitable place. Too hot, suffocating, you couldn't breathe there, and probably some toxic stuff in the atmosphere as well. Now, let me back off and say this. Remember I said the highest concentration of carbon dioxide of any place in the atmosphere, mostly carbon dioxide. What is our atmosphere mostly? Anyone want to hazard a guess? Nitrogen. About 80% nitrogen, about 20% oxygen. So very different from that. Where does carbon dioxide fit in our atmosphere? Say again? Okay, we breathe it out, but basically it's less than 1% or no more than 1 or 2%. So there's not that much oxygen in it, and yet by doubling a small amount, we greatly increase our greenhouse action. Okay, but it's not a lot of carbon dioxide. We have about 20% oxygen. We are the only planet that has anywhere close to that much oxygen. In fact, I don't know if any of the other planets even measure any measurable oxygen. Now, you hit a very good point there. We breathe out carbon dioxide. So why aren't we higher in carbon dioxide than what we are? Say again? Someone said something.
I was going to say, I guess because...
Say again?
Does the nitrogen override the...
Okay, what about oxygen you said? Is that what you said?
I said does the nitrogen override the carbon dioxide?
Okay, yeah, nitrogen's there. We breathe in nitrogen, we breathe it right back out. We don't use the nitrogen at all, okay? Nothing does, it just hangs around there, okay? I'm talking about oxygen, carbon dioxide. Why aren't we higher in carbon dioxide than we are in oxygen? Trees, exactly. We have green plants. And what do green plants do? They take in carbon dioxide, extract the carbon, and breathe back out the oxygen. If we didn't have green plants, we don't live. Because we don't have any other way of getting oxygen. Oxygen is a highly reactive gas. It's going to combine with something. The trees, the green plants, take out that carbon dioxide and put back oxygen. Yes.
But how do they put oxygen in the tank?
Well, I don't know exactly the process they do, but they separate the oxygen. My guess is through centrifuge, because it's a different density from any other gas. They probably spin it around, take out just that's oxygen, and then pressurize it in tanks. That would be my guess. They may have a better way of doing it than that. But yeah, it's a manipulation to do it, definitely. And I'm not sure that it's 100% oxygen either. I know people who need O2, that may only be like 50% or 75% O2. You know, it may be, it's not pure oxygen. Yeah, that would be pretty rough stuff. Huh? It's what? It's liquid in the tank.
Yeah.
And that would be another way. I didn't even think about that. Cooling it, it comes out as a liquid different from any other gases. So when it comes out, then they separate the liquid out, and then probably put it in tanks, and then let that expand when it sublimes, okay, or evaporates, I guess. So, don't want to go there, okay, ever, okay. Want to go there to study, but not to be on that surface of that planet. All right. we skip Earth because next chapter we talk more about Earth, and then the next 4 chapters we talk more about Earth. 4 after that we do. So let's jump over to Mars. Okay? Let's get again. Here's the sun. There's Mercury. There's Venus. There's Earth. And then there's Mars. Okay? About half again as far from from Earth as Earth is from Sun. Okay? So it's 1.5 astronomical units from the Sun. Okay? Now, and by the way, the Earth is how far from the Sun? How many astronomical units? 1. Because that's how do we define an astronomical unit? The average distance we are from the Sun. So we're 1. So Venus is 0.7, we're 1, they're 1.5. Okay, so Venus is 0.3 from us, and Mars is 0.5 from us. And Mercury was about 0.7 from us. Okay? Now, Mars has geologically active regions, just like I suggested Venus does. The Moon has had in the past. We have. Ask anyone living on the Big Island in Hawaii. What's going on there? Yes, the Kilauea volcano, which has been for many years, like decades, the most active volcano in the world. But it's not one of these that just erupts big time and does like that. It just oozes out lava all the time. It has for the last 35, 40 years, just been oozing lava. Until recently, new fissures have happened. Things are getting blown into the air. It's just not quite like a cone volcano, but still very active. Well, Mars has inactive volcanoes, okay? A lot like the Moon does. It has canyons. What forms canyons? Like, what's our most famous canyon? Grand Canyon. And what formed the Grand Canyon? Say again?
Dirt.
Well, that's what, yeah, it's made up of, but what made it a canyon rather than a flat plain? Say again? I can't hear it.
It's something like
Yeah, something near it.
Well, like earthquakes,
What?
earthquakes.
Not an earthquake. The Colorado River is all erosion. Every bit of the Grand Canyon is caused by erosion. Okay? Colorado River running through and runs through fast and hard and is just eating away, and it's continuing to eat away at the bottom. Okay? Well, what would form a canyon on Mars then? What does that suggest? That maybe at one time, anyway, they had water. Or how else the canyons form, we don't know, but it does appear to have canyons. It seems to have terraced plateaus near the poles. We're building up toward the poles, okay, terraced. Flat regions pitted with craters. Now that's not a crater, that's where something landed, and we made that mark. We can't really see in the pictures here. So what would the craters suggest?
I guess meteors.
Yeah, things have been hitting it, and why did they form craters that we don't have on Venus or much on Earth either? Say again? Okay, well, they don't have much to do with the cratering. They look maybe like craters from above, but we have atmospheres. Mars has an atmosphere, but it's pretty thin. So many of those meteors and asteroids and other things have impacted Mars. Not as much as the Moon or Mercury, because it's just terribly crazy, because there's absolutely no atmosphere on those. So this one does have a thin atmosphere. Craters, thin atmosphere, those relate. And I guess I misstated before, its atmosphere is also mostly CO2. Venus certainly is. Heavy, dense atmosphere of CO2. Mars is mostly CO2. What's in between Venus and Mars? Earth. So who knows? Maybe we should have had and maybe did have a high CO2 atmosphere until we started getting green plants. We had to have the green plants before any animal life could exist. So maybe we would have been right there with high CO2 atmosphere too, except for green plants. Constantly taking that out of the air and putting more oxygen in. Okay? What's that? CO2 is carbon dioxide. Carbon dioxide, CO2. Now that to me, for it to be on Venus and to be on Mars, I always thought carbon dioxide was made from living things breathing out. I didn't know carbon dioxide, well, that's not quite true. When you burn wood, you make carbon dioxide. When you burn coal, you make carbon dioxide. When you burn fuel oil, you make carbon dioxide. Anything that's carbonaceous. The reason we breathe out carbon dioxide, we burn sugars and starches, maybe some proteins and fats. What we're burning, the carbonaceous material, it comes out as carbon dioxide, because what burning is oxidation. It may be slow oxidation in us or rapid oxidation if it's a burn, but it's always oxidation. Oxygen combines with just about everything, including carbon, big time. So I thought carbon came from living material. No, there's plenty of natural carbon out there. So we knew that, didn't we? In the last chapter, what's the final product of many of these stars when they finally are dead? Especially the smaller ones? Chunks of carbon. Okay? That was what was left over. So yeah, there's plenty of carbon out there, and oxygen, if it was there, is going to combine with it. Okay? Now, strong evidence for liquid water in the past. There's one of the strong evidence, the canyons. Okay? There must be other, or else we wouldn't have said this. So if there was liquid water in the past, maybe there was some type of life there. Was it upright, big life like us? Probably not. We're probably talking microbial life, microbes, maybe fungi, maybe just little stuff. No evidence that there was ever any human-like life there. In fact, they have no evidence there was any life there. All they have is strong evidence for liquid water that suggests maybe you had life, but we've not found any evidence of it. And numerous space probes. Now, before we leave this one, let's just take a look at what some of these are. Okay? Now, it says strong evidence for water in the past. Well, I mentioned canyons, but here's more evidence. Okay? And this is really hard to see. But you have a sharp face over here and a gradual face on this side of the rock. Okay? And usually what causes that is water flow. Okay? They don't have much atmosphere, so it wouldn't have been wind effects. It seems like it would have only been water effects. So in addition to the canyons, you have other features of rock that we've taken very good pictures of, and it really does indicate or suggest something like water flow went on there. Okay? I'm sorry? Yeah, but the volcanoes have been inactive for quite a bit of time now. So, yeah, but we don't know. You're absolutely right. It could have had water before the volcanoes and they messed things up, or it could have been once they settled down they had water. But here's the key: very thin atmosphere. So water vapor, when it went into the atmosphere, it may have lost it. It may have just drifted out into space. Okay? They think that these polar regions might have ice underneath it because it's 1.5 times as far from the sun as we are. The poles would get the least amount of direct solar radiation, so it could be there's ice there. You don't see it on the surface, but it could be underneath the surface.
But Earth made of total water.
What's that?
I said Earth is made up of water, so.
Okay, our surface is.
Yeah.
Most of the Earth, the solid part, and inside the liquid part is mostly iron. Way
On the solid part, we got heat.
What's that?
I said, up on the surface though, part, we got heat.
Yeah, we do. Okay, and here's another thing. Most of the, and we'll get this in the last chapter we do, most of the water, certainly most of the water is in the oceans, but most of the fresh water, you might say, is in, say again? Glaciers, you're absolutely right. But also, you have ponds and lakes and things that have fresh water, but you have a lot of subsurface water. We call those groundwater. And that's, most of the time you can drill a well just about anywhere, and at some point you'll hit water. Okay? So we have lots of groundwater. Well, Mars probably wouldn't have groundwater, but it may have ground ice. Okay. What's that? Yeah. However we get it, yeah, we're going to pay for it. Now, I grew up on a farm, and there we drilled the well. We had to pay for drilling the well, so all we had to pay for was the electricity to pump the water out. Because our water, so it wasn't paying for the water, it was paying to pump it out, and it's pretty minuscule. Okay. Now that is one place we took a sample of the Earth's surface there. So that was man-made. So we weren't actually there to make it, machine-made. But the surface of Mars. Guess what? What is the color you call that? This one, red? Red is that surface? That's what Mars is called, the red planet. And that's really where it got its name. In Greek or Roman, I think maybe Roman mythology, the god of war was Mars. Okay? Red, bloodshed, fighting, anger, that was Mars. So they called it red planet. Now, if you look out at many of the fields in Alabama and Georgia, what do you see? Soils. What color soils? If you see a farmer, preparing his land for raising crops, what color soil do you usually see? Okay, yeah, there's a lot of brown soil, but especially drive over to Georgia. On our farm in Georgia, plow a penny field, the vast majority is going to be red. Georgia red clay, right? The red comes from the oxidation of iron. What else is reddish color associated with iron? Especially if iron's been sitting outside for very long. Rust, exactly. That's what gives the red color. That's why the surface of Mars is mostly red. Oxidation of the iron. So their composition is probably not too far off from ours, a lot of iron, and it's been oxidized, and ferric oxide is reddish color. There's another oxide that's bluish, blackish color, and that's ferrous oxide. But the ferric oxide is reddish. That's where they get their color. All right. Now, we skipped something in between Mars and Jupiter. Anyone know what it was we skipped? We're going to come back and talk about it later. What's in between Mars and Jupiter? It's called the belt. The what? The asteroid belt, exactly. Okay? So we'll come back and talk about that when we talk about the smaller bodies. So we're jumping over the asteroid belt, going out to Jupiter. Okay. Let's get this again. Here's the sun. There's Mercury. There's Venus. There's Earth. There's Mars. And that's 1.5 times, 5 times, there's Jupiter. Asteroid belt's in between there. Okay? In fact, that suggests that maybe the asteroid belt was supposed to have been another planet in there, because there's a huge jump between 1.5 astronomical units of Mars to 5. I mean, that's more than 3 times as far. And that's where Jupiter is. It is by far the most massive planet. 318 times Earth's mass. That's big. Okay? We are the biggest of the 4 interior planets, called the terrestrial planets, the rocky type planets. Jupiter is 318 times more massive than we are. And it's mostly hydrogen and helium. with an iron silicate core. There's that iron again. We're mostly iron, okay? Our surface is silicate, largely. Where do we get the hydrogen and helium? Where have we run into hydrogen and helium before? Like the last chapter. The sun and the stars are made mostly of hydrogen and helium. Remember, the hydrogen fusion is what powers the stars, okay? Well, Jupiter has this. Not that much hydrogen or helium in our atmosphere, in Venus's atmosphere, or in Mars' little bitty atmosphere, and certainly not on Mercury. It doesn't have an atmosphere. And here's the idea. When the sun was doing all of its things of forming, it probably blew off a lot of its gases, and they went out to the last four planets. Went right past the first four and went to the last four. And they were the lightest of the gases, too. But all of them have the iron silicate core. Okay? So, that's what Jupiter is made of. Let's see a visual of this. Now, we're going to see something later, next chapter. It'll look a lot like this. Okay? Earth has an inner core, and then things out here and things out here. The things are different, but the iron silicate core of Jupiter, just that core is still 10 to 15 times the Earth's mass. That's a huge core. I mean, that would make 10 or 15 Earths, just the core of that. Then you've got all this other stuff out here, and this is a liquid metallic hydrogen, which is a weird kind of phraseology. Okay? Now, if you got hydrogen and helium out here, what would make hydrogen liquid? What would make hydrogen liquid? Two things. And they kind of contradict each other, but two things would make a gas into a liquid. Anyone think what they would be? Okay. How do you make a liquid into a solid?
Water.
Okay. Water is one. How do you make liquid water into solid water?
Ice. You freeze it.
You freeze it. You take away heat. Okay. So if it's very, very, very cold hydrogen, it may become liquid. Okay. A liquid hydrogen is really, really cold. Okay. Now you would think that this core, with all the pressure and on it, it would be pretty hot. And it may be, but this could be. But there I said the other word. A gas takes up lots of space. If you push the molecules closer and closer together, you could make them form a liquid. But that's pressure. So I'm guessing it's either the pressure, huge gravitational pressure here of Jupiter. I mean, it's enormous. So that may be what makes the liquid metallic hydrogen. Okay? And that's about 35,000 kilometers thick of this liquid metallic hydrogen. Ooh, that's a lot. Okay? Then you have liquid hydrogen here. Now I can easily believe that because of low temperature, because there's nothing to keep it warm. Okay? It may be this in here is pressure and temperature. This is temperature. And then the atmosphere is mostly gaseous hydrogen, gaseous helium, gaseous ammonia clouds, about 500 kilometers thick. The liquid hydrogen, 20,000 kilometers here, and the liquid metallic hydrogen, about 35,000 kilometers. I mean, we're talking about huge, huge, huge planet. It's so huge that when we do go to the planetarium, the odds are you'll hear him talk about the sun being here, Jupiter here, and that sets up a mathematically plausible and possible thing. A lot of the ways the rest of the atmosphere is structured is because of the huge gravitational field of the sun, and then the really big gravitational field of Jupiter as well. Earth's gravitational field doesn't hold a candle to this one. Now, yes.
How are we getting to the planetary?
How what?
How are we getting to the planetary?
How what?
How are we getting there?
We can do it a variety of ways. I can get a van most of the time, but it only carries, I think, legally 7 students. Okay, so about 7 students can ride with me. Others can, if you don't mind taking your own transportation. If I really need to have another vehicle, I might be able to get another instructor to get another vehicle, but we don't have anything that carries much more. I think there may be a 15-passenger van, but I'm not sure the insurance will cover 15 people in it. But anyway, we'll get there. If we need to, I'll get a vehicle. I usually do. But a lot of times people say they want to drive their own vehicle.
Where is it at?
It's on Sanford campus.
Oh,
You know where Sanford is on
Lakeshore?
Lakeshore, yeah. Right. So a lot of people live near that, so they don't want to come back to campus, so they don't like to drive there directly. Okay? And if you can carpool and stuff like that, sometimes no one wants to go in the van, so I'll drive and I can take 3 or 4 people in my vehicle. But I'm coming back to campus, or at least going back to Birmingham. I'll come back to campus if we need to. So, but we'll find a way. We always work it out. Okay, that's coming up not after this chapter, but after the next chapter. Okay. Yeah. Question. Okay. All right. So there is how Jupiter seems to be huge, and that's why they call it a gas giant. If you think about this, that 500 kilometer thick cloud is all we see, okay? Now we see lots of storms in the cloud. We're going to see that in the next slide or so. But then we have liquid hydrogen here, and liquid metallic hydrogen there, and then an iron silicon core, which may be mostly solid, but I would expect it would be quite hot, okay? Because of all the pressure above it. And here is a picture of Jupiter. This is fairly close to the equator here, and this is called the Great Red Spot. It is an enormous storm that, as long as we've been looking at Jupiter with cameras and telescopes and things, we've seen this, okay? So it's been going on for centuries. One storm, and it seems maybe to be decreasing a little bit in intensity. So maybe one day the Great Red Spot won't be there anymore. That storm will have died down. But it's been a whopper of a storm, okay? So Jupiter has a vicious atmosphere. I mean, there's storms and different temperatures and bands, and it's a very active place. Very active place. I thought there was going to be another picture, but it doesn't show up. Okay. So, what I was saying, a very dynamic atmosphere. It's changing all the time. Maybe not changing composition, but stormy, rushing winds, it's a very active place. Mostly, like we said, hydrogen, helium, ammonia. Does anyone know what ammonia is? What? Like a gas? Is that what you said? Yeah, it is a gas. It is for sure. But we use ammonia to clean floors. Yeah, cleaner. It's a pretty strong smelling cleaner too, isn't it? The first part of this is amine. It's a nitrogen source. It's NH3 is what ammonia is. Nitrogen with hydrogen, NH3. Now the cleaner is NH4OH, which is ammonium hydroxide. It's dissolved in water, so you get ammonium hydroxide. But it's nitrogen. I think of nitrogen as coming from living things. because nitrogen is what builds our muscle, and trees and other things have things in it too, but that doesn't mean that's the only place it came from. Methane, I think of that as one of the carbon compounds that comes from emissions from living things, but not necessarily. Methane is CH4, carbon with hydrogen. And then water. Jupiter has water in its atmosphere, so not surprising that probably Mars one time had water. Okay? The water in Jupiter's atmosphere, I would guess, would be mostly ice crystals. Okay? Because it's cold. It's really cold. Remember, 5 times as far from the sun as Earth is. Okay? So it is very, very cold out there. The inner part probably is quite hot, but the surface has to be very cold. And so you have different temperatures, different materials, different speeds of gases moving around, and that's what creates these huge storms like the Great Red Spot.
So do they have any kind of forms that people live on Earth?
What's that? No one could live on Jupiter because if you think back of it, it doesn't have a solid surface. Okay? It has an atmosphere that's all gases, and then this here is liquid, and that is liquid metallic. That would be the only solid. You can't live down there. Okay? So yeah, no way to live there. So when I say if you're on Jupiter, you wouldn't be on Jupiter. You could be in Jupiter, but you're not going to be on Jupiter. Okay? Sort of a scary thought. Okay. Now, large system of varying satellites. The most of the moons in the solar system are around Jupiter. Okay? Let's back up a moment. We didn't mention the satellites of Mars. We said Mercury has how many moons? 0. Venus has how many moons? 0. Earth has 1. And that may have been broken off the Earth. Okay? Mars happens to have 2. It's a pretty small planet, and it has really small moons. But what's the next outside of Mars before you get to Jupiter? The asteroid belt, which is chunks of material flying around out there. I wouldn't be at all surprised if a couple of asteroids didn't get a little too close to Mars and they became Mars moons. Okay? And I really wouldn't be surprised if his asteroid got a little too close to Jupiter and they make up. I think Jupiter has in the neighborhood of around 50 or so moons. Okay, it's incredible. Now, I'm just guessing 50 or so. Okay, I'll see if it actually has it in here. I just noticed I skipped right over example 15.3. This is back on Venus. How many times would a space probe on Venus' surface have gone around the sun if it had been there 30 Earth years? That's a weird state question. What they're getting at is Venus' orbital period is basically 2/3 of a year. Its rotation period is almost a year, 243 days, which is longer than its orbital period. That's 62, about 2/3 of an Earth year. So you take 0.62 and multiply it by 35, and that gives you about 48 trips around the sun. Okay. Example 15.4. You don't have to do these. It's just to give you an idea. How many times has Jupiter rotated on its axis in the last 24 hours? We'll go to Jupiter. Why do they pick Jupiter here? We haven't talked about Jupiter yet. But if you go over to Jupiter and look at its rotational period is only 9 hours. That's a huge planet who's rotating in only 9 hours. We're a much smaller planet and we rotate in 24 hours. Okay? So its you got 9 and 9 is 18, so that's 2 Earth days there, plus almost half of another. So that's why they say that. So, hey, guess what? That also contributes to the very active atmosphere. What makes for winds here on Earth? The fact that the Earth is spinning with the atmosphere around it. The atmosphere doesn't stick with the Earth. It sort of floats on top of it. So near the equator, when you're spinning, the Earth is spinning like this, the winds are generally easterly winds because the Earth is spinning here, making the winds appear to come from the east. Really, the Earth is spinning under the wind. But then when you get up further, like where we live, the winds come around because they picked up speed from the spin of the Earth, and then they're going faster than the Earth, so up here they are from the west, and from the southern hemisphere they would be from the west. At the poles, who knows what's going on. So if you think about that Jupiter, as huge as it is, as big as its diameter is, as big as its circumference is, if it's spinning as that fast, it's got to have some really major wind motion going on there. I mean, incredible. No wonder the storms are fierce there. Okay? Now, let me see if I can find in the thing, because every edition of the book, I think they probably have found. So, oh, I was looking at the wrong picture. There's a great picture in the book they didn't have in our slide set, and this is a lot like. If any of you looked at the file I put out there on Blackboard under course handouts and more, or Dorothy found the title, but there's a file I put there called Space Objects in Perspective. Go to it sometime and look. It's pretty fascinating. And the first picture, one of the early pictures looks a lot like this. Okay, there's Mercury, relative size of Mercury. There's relative size of Venus, almost the same size as Earth, not quite. There's our moon, which is almost the same size as Mercury. Then there's Mars, which is bigger than Mercury, but quite a bit smaller than the Earth. And this shows one of Mars' moons, just a tiny little speck there. No, actually, that's not. That is actually, I read this the other day. It's the dwarf planet Ceres. And it's not one of the moons of Mars. It's actually a dwarf planet that lives in the asteroid belt. Okay? So that gives those 4 inner planets. Now the placement are nowhere close to right. These are just taking the pictures and imposing them near each other. Okay. If the noontime surface of Mars can reach as high of 20 degrees Celsius. What is 20 degrees Celsius? Any of you know? Give me a reference. It's about room temperature. We are really close to 20 degrees Celsius. What does it say there? 70, 72?
73.
73. Okay. 68 is 20 degrees Celsius. That is the hottest noontime temperature you would ever reach on Mars. A cool, pleasant 68 degrees Fahrenheit. Okay? It says, is that warmer or colder than a typical room temperature of 72 degrees? It's actually cooler. So we cool our room outside. It's way hotter than Mars would ever be. Okay? And 72 is about 22 degrees Celsius. You would have had to have had the earlier stuff to do that, but just to give you a general idea. Mars' coldest temperature, on the other hand, are around a negative 140 degrees Celsius. What temperature is that in Fahrenheit? That's about negative 220 degrees Celsius, Fahrenheit. So it's very, 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 very cold. Now, there's another little blurb here in your book. Passed over these, I didn't mean to. A case study, is it worth the cost? Now, if you wanted to expand on this, that could be maybe a paper topic. Of course, you can't get the information from here. You have to go elsewhere and get it. But if that's something that's of interest to you, is what we're spending on space worth it? Okay. By the way, do any of you own anything with Velcro on it? Second, Velcro. Velcro. You don't own anything with Velcro on it? Not with you, but I mean, do you own it? I mean, not wearing it now. Yeah. That's why all of us have something that has Velcro in it, okay? Guess why that was developed? To keep things from flopping around in a spaceship and hitting people in the head. Because there's no gravity there, this would not sit on the table, it just float around. I wouldn't want to get hit in the head with that, or with a stapler, or anything else, by a computer, So they developed Velcro. So there's been lots of very practical, useful things that have come out of the space program. You might say, it's not worth it. Well, we've also gained a lot of knowledge. So anyway, I'll let you look at that. Let's look at example 15.7. How fast would a rock falling from a 60-meter high cliff on Mars be traveling when it hit the Martian surface if the acceleration due to gravity, G for Mars, is 3.8. Now, we haven't talked about that either. That was in an earlier chapter. On the Earth is 9.8. So this is a little bit more than 1/3, and it asks you to use an equation 3.5. So we're not going to do that, but it would be traveling about 21 meters per second. If it was here on Earth, it would be way faster than that. How long would it take that falling rock to hit the ground? And again, you'd need formulas and equations from a different chapter. But go from 60-meter high. And by the way, let's just get a perspective of this. This room is about how many meters? I'm close to 2 meters tall and almost another meter above me. You could almost put another yardstick. So let's just say that each floor of this building is 3 meters. And one part of the building is 3 floors. So that would be 9 meters, right? So a 60-meter cliff would be, let's just say 6 times 3, 18-story building. So let's round it to 20. A 20-story building, if you drop something from the top on Earth, get there much faster. There on Mars, it would take more than 5.5 seconds. The gravitational field of Mars, because Mars is so much lighter, smaller planet than Earth is, much, much slower. Okay. Now let's get to Jupiter, some of the pictures here. And these are fantastic pictures of Jupiter. Not in our book, not in the slide set, because that was a previous book. We've gotten far better pictures since then. This shows the iron silicate core, shows the same things we did earlier, but here's different pictures of that great red spot. Doesn't look all that red here, but like I said, it's spinning so fast, its atmosphere is in turmoil, and that's what creates part of the reason for all those storms. Okay, this next picture, I think we have, another picture. Now, this is the great red spot. This is a big white spot. There's the great red spot at the top, okay? At the top, that's a very violent storm. The white one is a very big storm too, but that's probably a snowstorm, okay? The red could be coming from heat, coming from below. This is icy stuff, coming from the surface. So, violent place. Can you imagine the winds in between these? These are probably fierce winds. Okay? All right. Here's what I was going for. Does anyone know what these are? Moons of Jupiter. These are just 4 of them. The 4 biggest moons of Jupiter. And they have a special name, these 4. Galilean moons. Now, why would they call them that? Anything to do with the Sea of Galilee? No. Okay? What they have to do with is Galileo, who built the biggest, strongest, most efficient telescope of his day. Someone else had actually developed a telescope. He had read about it. He tried to build one himself. He thought of several ways to improve it. So suddenly he had the most powerful telescope that anyone had ever seen. And when he looked at Jupiter, he saw these 4 moons. Those aren't all of them, but those are the 4 biggest ones. And they have been named. I'll try to get them the same. Yeah. Okay. From left to right, they are Europa, is that first one upper left. Ganymede is the smallest of the 4. Callisto and Io. Wait, did I get them right? No, I'm sorry, I missed Io. Io is the first one. Europa is the smallest. Ganymede is the biggest. And then Callisto is the last one. Io and Europa are about the size of Earth's moon. Io and Europa, the 2 small ones, are about the size of our moon. Okay? The next 2 are even bigger. Ganymede and Callisto are slightly larger than Mercury. These are moons. Mercury's a planet. These 2 moons are slightly larger than Mercury. These are some big moons. Big, big moons. Now, let's go back on this. Remember, Earth is so tiny compared to Jupiter. I mean, just the core of Jupiter still contains how many Earths? 10 to 15? Right there. Iron, silicate core, well, 10 to 15 Earth masses are probably a lot denser, okay? But 10 to 15 Earth masses just in the core of Jupiter, okay? So Earth is so tiny compared to Jupiter. And yet, Earth's moon is about the same size as these. That makes our moon, relative to us as a planet, the biggest ratio there is in the solar system. Our moon is way too big for our planet. That's another reason they think it may have broken off of our planet. Okay? It's way too big. It wouldn't have formed this way. Now, what I was trying to do originally, I got carried away with other things, is here it is. Nonetheless, the giant Jupiter and its system of nearly 70 moons. I said in excess of 50. I was thinking 70, but I thought that's way too many. No, Jupiter has nearly 70 moons. Okay? They almost seem like a smaller version of the planetary system of a solar system, with the sun in the middle and planets around it. You have Jupiter in the middle with 70 orbiting bodies around it. Now, if you go back to the very beginning of the chapter, or very close to the beginning, you'll see that well, I thought it was in here. I know I've read it, and I just can't lay my eyes on where it is. And they talk about the smaller bodies. And I cannot see it. But it's something, if I'm not mistaken, it said something on the order of 100 moons in our solar system. Now, I'm remembering that, but I don't know if that's absolutely true. So that means Jupiter itself has 70 of those 100 moons. That's a bunch of moons. Okay. These are the 4 biggest ones. 2 of them bigger than our moon, 2 of them bigger than Mercury. Wow. Okay. Now, even though Jupiter is so much bigger, it's not nearly as dense as Earth because it's mostly gas and some liquid. So it's not nearly as dense. That core may be dense, but the rest of it isn't. Okay. Now, there's something mentioned in your book that's going to be mentioned in a later chapter in our book. Oh, maybe it's later in this chapter. I'm going to mention it now because it's here. There was a comet that made the mistake, it was flying where it was, happened to get too close to Jupiter. And Jupiter's huge gravitational force pulled it in, and you see the fragments, the trail of the fragments in Jupiter's atmosphere. Like I say, it doesn't land on Jupiter, it just goes into Jupiter. And these were very cold spots, and they went very dark compared to the rest of it. Now this is an ultraviolet light, so you can see them better. And here is infrared, I think, is at the bottom. And the picture was made from the Hubble Space Telescope. And you can see where all the huge gravitational field of Jupiter first destroyed the comet, pulled it apart, and then the fragments of it hit the surface. And you can see those here. Now, here's another example. Assume that one of Jupiter's moons receives the peak solar energy over a 10-hour period. How much energy is heating 1 square meter of that? You would have to know a lot more information than we have. So let's skip that all the way. Go back to these 4 here. Ganymede being the largest. And you'll notice here in the book it says Ganymede has valleys, ridges, folded mountains, and other evidence of active geologic history. So in other words, plate tectonics. I mean, that's acting almost like a planet, okay, as far as the characteristics of it. And this comet Schumacher-Levy, the one that got too close to Jupiter and is no more, you know who the first person who saw the evidence? He was not a professional astronomer. He was a guy who just had a telescope and liked looking at the heavenly bodies. He decided one night to look at Jupiter and said, wow, what are those spots? So he called the professional astronomers and said, what are those spots on Jupiter? They said, hot spots. They looked and they saw the same thing. So he was the first one to detect it. He was an amateur. He was just someone enjoying looking through his telescope. So he made use. Okay, now the Hubble telescope took these pictures, but his telescope was just a little one. Hubble telescope's the one out there in space. It gets much better pictures because it doesn't have the atmosphere to go through, and it's huge. It's monstrous, and they can figure out ways to get it to take exactly what you want. It's not an easy process. Okay. All right, I won't go into any of the others. So let's move from Jupiter. What's next? Okay. See, we've been going, what, about an hour and a half? And we've still got about an hour to go, right? Do we need to take a break? Okay, let's take a real quick break. And I do need to call roll again because I was supposed to call roll. No. I'm doing call roll at 1:50, and it's already past that. So let me mark the roll again since we're here. Okay, Ed's still here. Tyus didn't come in yet. I'll still give him time to come in for a while. Cassidy's still here. Jessica's still here. Christy's still here. Chris was here. Guy's not here. Adam's not here yet. I missed somebody. Taylor's not here yet. Adam's not here yet. And Justin's here. Jordan's here. Lauren's here. And Jacory's here. Okay, so take a quick, keep it less than 5 if possible. And I will go take a quick one myself. About dehydrated. At the doctor's in a rush here as fast as I could. They just don't get any water.
Chrissy,
I did want to tell you, today's probably not so bad. Thursdays are usually worse. One of the results of my doctor's visit today was that my white cell counts, which is what the treatment is knocking down, they're still really low, which is good because it's knocking out the bad stuff. But the bad news is it's also hasn't rebounded with the red blood cells yet. So I'm still anemic and low hematocrits and stuff like that. So that's why toward the last half of the class, I just start running out of energy. Sorry about that. But and I got another class after this one. So that's Tuesday and Thursday. Monday and Wednesday. I'm through teaching at 1:40, but still got lots of stuff to do after that. All right. So there's Jupiter. Any questions on Jupiter? And see, I called the roll. I think I marked everybody, even though you were still out. Okay. Let's move on to Saturn. Now, when I say Saturn, what do you picture? The rings. Saturn is the most unusual looking of the satellites because it has those big, beautiful ring structure around it. Actually, Jupiter, Uranus, and Neptune all have rings, but nothing coming close to what Saturn's is. So that's one thing that's distinctive about Saturn. Other things, okay, now get this. Sorry if I'm boring you to death with this. This is the Sun. There's Mercury. There's Venus. There's the Earth. There's Mars. There is Jupiter. Okay? Now, almost twice as far as it was from Sun to Jupiter is where you get to Saturn. I mean, every planet is almost doubling in the distance. It was more than that for Mars to Jupiter, but from Jupiter to Saturn is almost double. It was 5 astronomical units from the Sun was Jupiter, almost 10, 9.5 astronomical units to Saturn. Oh, let's go back to Jupiter a minute. Sorry. Where does Jupiter get all those moons? What is it right next to? The asteroid belt. I bet you bunches of things that used to be asteroids are now moons of Jupiter. Probably where Mars got its 1 or 2 moons, and more than likely Jupiter has ripped off asteroids and made them their moons. Saturn is way out there. Now, you can't have everything in the rings as moons, but it has rings and rings and rings of particles. They could be dust particles, ice particles, just all sorts of things there. And here is the other feature of Saturn beyond, okay, number 1 is beautiful rings. I would say number 2 is the second largest planet, okay? Number 3, it's such low density. 0.7 times the density of water. What does that mean? If you had a big enough bucket of water, which you wouldn't, Saturn would float. Okay? It's a planet that would float in water. Of course, you wouldn't be able to get it in water. We don't have that much water. Okay? It's so huge. But its surface is very similar to Jupiter's. It's an atmosphere, liquid, hydrogen and stuff, and then other things. Very much like Jupiter, only much less dense. Okay? All right. Now, remember, Jupiter had around 70 satellites. Saturn has around 30. So I think my estimate of 100 total, way wrong, because there's got to be at least 120 or so moons out there. I just couldn't find it to tell. Now, Saturn's largest moon, fitting name, Titan. Remember the Titans? Okay, no. It's the only moon in our atmosphere, in our solar system, with a substantial atmosphere. Okay? So it could almost have life on it. You know, And I'm thinking it's even bigger than Ganymede. It may not be. It may be about the same size, but it has a substantial atmosphere. It's probably hydrogen, helium, and ammonia and that kind of stuff. So it's probably not sustainable of anything, but it does have a substantial atmosphere. I'm guessing probably more than Mars. Okay, definitely more than Mercury. Okay, so it has a substantial atmosphere. Okay. Now, here is a sort of close-up shot. I think this one was taken with the Cassini-Huygens. Made a very close approach to Saturn. It's a spacecraft, I think it was largely done through the European Space Agency. The European Union has a space agency now, and I think we participated in some of the science and stuff, but I believe that's where this picture comes from. Just incredible. I mean, there's different things in the different rings that I can't begin to tell you, but this ring is different from that one, and they're all different. Those are very different from the others. So there's incredible. I'm sure someone has some theories of why Saturn has this, but it's the only satellite or planet that has this beautiful exhibition. Okay. Our slide set has very little about Saturn on the pictures. In your book, there is a bit more. Okay? Now, you'll have to go back and check on this. But here's Saturn, huge, huge planet, second largest. And then they have a series of rings, and they name one of them Cassini. I guess he may have been one of the guys who first studied it. And it lists several of the other things here. There's some lighter colored rings that you probably can't see here. And they name these the F ring, the G ring, the E ring, and Titan, the big moon, is way out there. Okay, here's some other moons in here. Now, they don't line up like this, but they're just giving. There's Mimas, and it names several of them. Titan is way, way, way out there. Okay, so it's not part of the rings of Saturn at all. Okay, it's way outside. Okay. And actually, this slide is too old because it says Titan is the only moon with a substantial atmosphere. I just noticed in your book, now I've lost it. I just saw it. Yeah, here it is. On page 391, first column, second paragraph. Cassini, which is the Cassini-Huygens space mission that was international in nature, and it was launched actually, I think, in by the European Space Agency, but we were all participating in it, has also discovered that Saturn's icy moon Enceladus, I guess is how you say that, and in that picture I was just showing you, that's about outside most of the rings, just in that, well, not the last ring, but here's a ring here, and that's where Enceladus is. It's an icy moon. It also has a significant atmosphere. So it's not, Titan isn't the only one. There's several others that do too. But Cassini discovered that. Enceladus is, however you say, the Enceladus is too small to hold onto an atmosphere. That doesn't make sense. It says it has one, but it says it's too small to hold onto one. So it must have continuous source that may be volcanic geysers or gases escaping from the interior. So that's interesting. Okay, so it doesn't have a sustainable atmosphere. All right, and there's several other interesting things there about Cassini. Nothing replaces reading the chapter. Okay, the slideshow can't show everything that's there. Lots of really interesting stuff. Now we move from Saturn to the last two. Okay, Saturn, 9.5 astronomical units, almost 10. Okay, Uranus, double that. So they're not just getting equidistant, they're doubling every time what it was the whole thing. So inside Uranus atmosphere thing, you have to go halfway inside that circumference before you get the whole rest of the solar system, okay? And then Neptune is not quite double that, up to 30 astronomical units. These are way, 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 way out there. These are the outermost giant planets, and we often call them the gas giants. Very similar internal structures, and pretty similar to what Jupiter and Saturn were, though. This is a picture of Neptune, I'm pretty sure. Yeah. I'm pretty sure that's Neptune. Nearly the same size as Uranus, but is more than twice as far away from the Sun. And that doesn't quite agree with what they say here, but it's awfully close to twice as far. Way, way out there. Now, this picture that you have in your text of Uranus gives something away. The Sun is over here. Here you see the ring around Uranus. Like I said, actually all four of the gas giants have them. Not nearly as significant as Saturn's. But what do you notice about the ring? It's going like this. That means the rotation of Uranus is almost at 90 degrees to its circle. So that is really bizarre. I mean, we thought Venus was strange. It turns backwards. Uranus' rotational axis is almost in line with the distance to the Sun. So it's spinning like this. And as it goes around, so I can't even picture how its sunrises and sunsets are, because half of its year, its pole is away from the Sun, spinning like this, so it doesn't have any sunrise and sunset. The other half is facing it. So it is really, really bizarre. But that far out there, it can do just about anything it wants to. It is way, way, way out there. Now, and that's about all they say. Okay? About those. Recently in the news, have any of you been following this at all? They think they have postulated, several really seriously believe there is another planet out there. Okay? Now, as it is, we've only known about Neptune for a few decades, I think it is, or maybe a few more than that. It's way out there. You never see it except with a really strong telescope. It's way, way out there. Guess what? They think there's some evidence. Gravitational fields and things like this is yet another one out there somewhere. And if you think about Neptune, that far out, how long is its year? How long does it take it to go around the Sun? Okay? Let's go back to our favorite table there at the very beginning. Neptune, the orbital period, 165 years for Neptune to go around. 165 years, okay? From the time it's closest to the Earth, on the same side of the Sun as the Earth, and it's not very close to the Earth, before it gets there again, it's going to be 165 years, okay? It's a long time. Now, if there was another planet twice the distance from the Sun as Neptune, that would be 60 astronomical units thereabout. It's so far out there, it's been there and we've never seen it. Because it's so far out, you don't see it well. And what if it's, okay, picture this. What if it's basically on the somewhere way out there on the opposite side of the sun from us, and whether what we're doing in here doesn't make any difference at all. It's going to have to get a full planet before we even have a chance to see it. If it's such that we're seeing its dark side, we'll never see it. So, it could easily be there is another planet out there. There's lots of indications it can be, but no one's found it yet. Okay, many of them think there is. Okay. Now, I just happened to notice this. I hadn't, again, this is a newish edition, and it's not on our slide set. But way early in the chapter, when it was talking about the dwarf planets, it mentioned, I think, 5 of them. Okay. They name some here: Eris, Pluto, Ceres, Makemake, and Haumea. So yeah, there's 5 dwarf planets. We know of at least 5 of them. And in this picture here, you see, and this is not to scale, I think I mentioned this before, there's the 4 terrestrial planets, there's the sun here, way bigger than anything imaginable in the solar system. Mercury, Venus, Earth, and Mars. Shows 1 moon of Earth, it doesn't show Mars. There's the asteroid belt, and there in the asteroid belt is Ceres, a dwarf planet, not nearly big enough to be a planet. Then Jupiter, Saturn, Uranus, and Neptune. And then out here is Pluto. And Pluto also has at least 1 moon. Okay? And then outside of Pluto, but not too far outside, is Haumea. Okay? And then slightly outside it is Makemake. And by then you're in what they call the Kuiper belt, which we're going to talk about in a bit. And then outside of it, you have Aries. Okay? Those are your 5 dwarf planets. Ceres in the asteroid belt, Pluto, Haumea, and Makemake. Makemake being in the inside part of the Kuiper belt, and then Aries, which actually looks like it's outside the Kuiper belt. Now, the reason I mention that is that's what we're going to next. Okay? I just saw the picture and thought I didn't point that out to you before. So let's move on to, and I'm not even going to get into these. They're examples. It's sort of like they make up something to do an example of to give you some calculations because we don't have enough calculations. Well, a lot of that stuff came out of the first half of the book that y'all haven't had, except for Justin. He could show you how to do these, but he doesn't want to, right? Okay. All right. So let's move to the smaller bodies of the solar system. Now, these consist of sort of 3 classifications. Okay? Comets is one, asteroids is another, and meteors. Okay? And I kind of find it obnoxious they use meteorites. Later they're going to give you some definitions. They really should be saying meteoroids. Okay? Comets, asteroids, and meteoroids. And I'll tell you the difference later. Okay? Now, yes?
Is this still chapter 15?
Say this again?
Is this still chapter 15?
Yes, it is. Yeah. This is all the solar system. We just covered the planets and some of the moons. Now we move to the smaller bodies, okay, that are not moons. Okay? Comets, asteroids, and meteoroids. I don't like to call them meteorites. Now, there's literally millions upon millions of them out there. And this is just stuff junk, particles left over from the solar and planetary formation. Now, we haven't talked about planetary formation yet. We're going to get to that later in this chapter. But we talked about the solar formation. Started as a mass of gases and got gravitational collapse. And then when it started fusing, then it was just going crazy, spewing stuff out and bringing stuff back and stuff like this. This is a lot of the junk that was spewed out when our sun was not at an equilibrium yet, okay? Left over from that formation. Now, this is the statement I told you early on might be confusing. The mass of the smaller bodies may be 2/3 of the total solar system mass. Now, what statement did I mention earlier? I really pointed it out to you that contradicts this one. If you go back to the very first page of the chapter, I think it's the first page, 15.1. On page 379, that last paragraph in the right-hand column, the sun has 700 times the mass of all the planets, moons, and minor members of the solar system together. So when you're talking about the solar system, more than 700 times of everything else is the sun. So the sun is not included in this, okay? It couldn't be. What they mean is the mass of the smaller bodies of the solar may be 2/3 of the total non-sun mass of the solar system. So all the planets and all the moons added together would only be 1/3 of the mass. That includes Jupiter, okay, and everything. The rest of these smaller bodies, there's so many covering such a huge area, they have 2/3 of the mass of the non-sun part of our solar system. Because the sun is 700 times everything else put together. So it can't be included here. Okay? Now, these other objects sometimes hit the bigger objects. Okay? And this was the comet Schumacher-Levy. This is the picture we saw in our text. In the older edition, the one the slide set goes along with, it showed this under the smaller, because it was focusing on the comet, not on Jupiter. Okay, now, I can't say for sure, but I'm guessing this is what that amateur astronomer saw and said, what is that? They focused in the Hubble Space Telescope on it, and they found out that's what it was. It just was a series of things. The comet Schumacher-Levy 9 got too close to Jupiter. The gravitational force just literally tore it apart, and the pieces hit the surface of the planet. Remember, Jupiter's spinning pretty fast, so as they landed at different positions. Okay? It struck Jupiter in July 1994. I just want to ask a dumb question. How many of you were born then? 1994. A few of you were. Okay. I wasn't. I mean, I was a long time. I was old by then. Okay. So, that's what one student in one class asked me how long I had had leukemia. I said, well, they discovered it in 1991. He said, whoa, that's longer than I've been alive. I went, yeah, I didn't want to hear that, So anyway, that's why I asked. Okay. So sure enough, this happened back in 94, and it was seen first by an amateur. It just happened to be gazing at Jupiter. He didn't see it happen, but he saw the spot shortly after it happened, sometime after it happened. Okay, so we have these classes. Let's look at them individually. Everybody got that? Let's look at comets. There are two sources for comets. Okay? There's one that's way, way out there. This is called the Oort cloud. O-O-R-T. Now, that name must be named after somebody, because I can't imagine anyone making up that name. So that could be a paper topic. Who in the world was Oort anyway? It sounds like Mork and Mindy's friends, but I don't know. Okay? The origin period of these long period comets are something greater than 200 years. So if you see a comet from the Oort cloud, You're not going to see it again. Probably your grandchildren or great-grandchildren might see it. Oh, yeah, Granddad talked about that. No, I don't think you'd even remember that, okay? Now, that is 30 astronomical units to 1 light year away. Now, remember, Neptune was right at 30 astronomical units, right? So this is anywhere from Neptune to 1 light year away. That is way, way out there. So our solar system covers a lot of space. Our sun's gravitational field, remember it's just an average sun, it covers up to 1 light year away. Now, a little bit closer than that, but overlapping partly, is the Kuiper Belt. Now, I don't know if I'm pronouncing it right. I think I've heard some people call it the Kuiper Belt, and that may be more correct. I actually heard one person, this is a lady at the Birmingham Southern Planetarium, was calling it the Jupiter Belt. I went, wait a minute, there's no T in there. You know, I thought I had it wrong. I went back and checked, and no, she must have had it wrong, and she did. Okay, she was right on most of her stuff, but she just mispronounced that. It's either the Kuiper Belt or Kuiper Belt. I believe the guy at Sanford calls it Kuiper. To me, it looks more like a Kuiper. I don't know. It's the origin of these short period comets. They're just less than 200 years. What's the most famous of them? Anyone think? Most famous comet? Not happened during your lifetime. Has happened during mine, though. It was Halley's Comet. Halley's Comet comes around about once every 70 years. And the last time it came around was when my wife was working at Fernbank Science Center, so she would have been a little bit more than 20 years old, and she was born in 57. So that was about 1980, late 70s, early 80s. Okay, so 70 to that would be 2040. Most of you will still be alive then. Doubt if I will. Okay, anyway, that will be. You might get to see Halley's Comet. The last time it came around, you needed a pretty good telescope and know exactly where to look, or binoculars, and know exactly where to look, and it was still hard to see. The time before that, it came much closer to Earth, and it scared the daylights out of people, because this bright light at night streaking across the sky. And the time before that, they thought the world was coming to the end. I mean, it was that impressive, or sometime before that. Okay, so the Kuiper Belt, I don't know why they leave these in reverse order. It's a disc-shaped region. See, the Oort cloud is all over the place, you know, sort of spherical. The Kuiper Belt is a disc-shaped region between 30 and 100 astronomical units from the sun. And that's why that picture I showed you before, just outside Neptune, and you got those other 4 dwarf planets in there, or 3 dwarf planets in there, Haumea and Makemake. Pluto, Haumea, and Makemake are in there. And then you had the Kuiper Belt with Ceres or whatever it was, just outside of that. I said it wrong. Aries. Ceres is in the asteroid belt. So the Kuiper Belt is sort of like the asteroid belt, only way further out there. Okay? Now, these things hang around way out there, and here's the key, and this came from, I always go blank on this guy's name. Laws of planetary motion. I don't know why I never can remember his name. But anyway, when a thing is far, far, far from the sun, it moves really slowly. When it's close to the sun, it moves much faster. Okay? You'll see most of the planets do that. Okay? But these asteroids certainly do it too. I mean, comets do it too. When they're way out there, they're moving so slowly it takes them forever. But when they come in faster, 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 and then go away and slow down again. Okay? The fastest speed is when they're near the sun because of gravitational pull. So something happens to them to force them, either they're moving in a regular, highly elliptical orbit, they have close and they go way out again. That's what Halley's comet does. I think that's what Schumacher's Levy 9 did, because it showed up periodically. But some of the others, they just take something that happens that they get too close or too far from something, and they get a gravitational nudge, and they start falling towards the sun. Okay? And they deflect some objects toward the sun, and once they get pulled toward the sun, they pick up speed, and then get slung back out again. Okay? Now, we've learned from that. When we send up spacecraft, we don't want to power them all the way from here to Mars or here to Saturn, and we sent them to Cassini-Huygens. I mean, we like to use things. So what we do, we'll send them, and if Venus happens to be close, we'll send them around Venus. They'll go around Venus a few times, and it goes sort of like, I don't know, when you were a kid, if you played Cracker Whip, and the person at the end would start going faster and faster, so they couldn't hang on anymore, and they'd fly off. Well, that's what we do. We send the spacecraft, they go around like this, and when they pick up a lot of speed, then we go. So we use the gravitational nudges, flipping away from the planet, and then leave. I need to take that off the board. I'll try to remember. I won't have time at the end. Let me take it off now. Just notice it's still here. By the way, does Miss Martin come in and tell you I would be a little bit later? No one came in?
But she came in.
Oh, she did. Okay.
Yeah, when I got here.
Okay. Yeah. I called her as soon. I couldn't call from the doctor's office because at Kirkland Clinic you can't get any phone service. No service at all. I couldn't do anything there, so I had to wait till I got out of the doctor's office. I called, and the first 4 or 5 numbers I couldn't get anyone in the office. I finally got her, and she said she'd come down. Okay. So we learned from that, and that's how we send spacecraft further out into space. But we have to time it just right to get it going in the right direction. But those people at NASA are pretty smart. Okay, so just the opposite of these gravitational nudges, deflection to the sun, they pick up speed and come in. Okay? And that's why some of them don't follow really regular patterns. All right, here is our best guess of how you picture this. Okay? There's the sun. You remember how massive the sun is? 700 times more massive than the whole rest of the solar system put together. Okay? That's it in the middle. Just really, really tiny. Okay? And this is the orbit of Uranus. There's the orbit of Neptune. There's the orbit of Pluto. Now, all the other planets are in here closer, but they get half the distance in there. So they didn't show the innermost planets. So that's why most of these are in a sort of a circle. Pluto's like that. Not a planet, a dwarf planet. Okay? And actually, sometimes it's inside Neptune, sometimes it's out. Most of the time it's out. Okay? Now, all that fits in this little space right there. All of this fits in this little space right there. Beyond that, you have the Kuiper belt, which is the disk around here, and then the Oort cloud, which is like this. So this is up to 1 light year away from that tiny little sun in the center. Okay? These are 30 astronomical units here. That's where we begin here. The Oort cloud covers all of that, and the Kuiper belt is the disk around there. Okay? That's just 30 to 100 astronomical units away. So that's no wonder that 2/3 of the mass of the solar system is in all this, and only 1/3 is in the planets and the moons inside of that.
So that's what's over Earth, and we're in that little dot space.
Yeah, okay, yeah. Earth would be just about, you couldn't hardly draw the circle around the sun because it would be too small. Because there's Uranus. Take half of that and you'll get Saturn, half of that you get Jupiter, half of that, no, a fifth of that you get Mars, and then a fraction of that you get Earth. So we'd be so close to the sun you can't tell us.
So that bright light is the sun.
The in the middle of that is the sun, and this whole thing is in that little space right there you can't even see. That's how big our solar system is. Our solar system is just an average little solar system. There are stars out there with probably 10, 15, 30 times that size of a system around it, and yet they're so far apart, and billions of those in our Milky Way, and billions of Milky Ways or bigger galaxies are all over the universe. It's just unbelievable. Okay, this is 50 astronomical units, so that would be like that. This is 30, that's 50. This is 50,000 astronomical units would be this. So that's almost a light year out there. Whoa. Unbelievable. So no wonder 2/3 of the mass of our solar system, not counting the sun, is in the smaller bodies. Okay? Added together. You just got so many of them out there.
So that's the reason why it takes astronauts forever to come and home.
Say this again.
That's the reason why it takes astronauts forever to come and home.
Well, astronauts what?
That's why it takes so long for them to come back.
Oh, yeah. And hey, look. We haven't even sent an astronaut any further than our moon. We haven't sent an astronaut to Venus. We haven't sent an astronaut to Mars. Nowhere close. We sent spacecraft to them, and we haven't sent a spacecraft. We have sent a spacecraft close to Pluto. And it's continuing on out, and it's just how long it's going to be able to run on its system before it dies, and then we'll not hear from it anymore. But we actually got pictures of Pluto. We may see those at the planetarium when we go, because he did one show for us one time. It's just unbelievable, what they found out about Pluto, things they had never known before. Okay. So let's look at the comet structure. Okay? Now, we're only talking about comets now. We're going to get to the other two later. Okay? Comets are small solid objects. But they don't look like small solid objects. There are two models, or there are some models, I won't say how many. One of these is a dirty snowball model. Okay? Why they call it that? Comets come from so far out, they're certainly extraordinarily cold, so they could actually have frozen water in them. Not just frozen water, frozen CO2. Now we know what we call frozen CO2. Anyone know the dry ice? Dry ice. If you've ever been to a rock concert and they have the things that look like smoke and fog that comes up in it, I haven't. I've seen them on TV. Okay, that's frozen carbon dioxide. Okay, frozen ammonia and frozen methane. Those are all gases normally, except water is normally liquid. These are frozen. These are really, really cold. So that's why. And then you have dusty and rocky bits. That's what makes it dirty. This is what makes it the snowball. This is what makes it dirty. Dirty snowball model. Okay. But if you were to see a comet like Halley's Comet when it comes around next time, if it gets close enough to see, you see basically a head, a very, very bright head. Let me get the slide up here. There it is. There's the head right there. That doesn't look like a small solid object. Okay, nowhere close. There's the small solid object is the head. What's streaming out from that are the tails. Okay, the comet head is a solid nucleus, and then around that is a coma. I never use that term in this sense except here. A coma of gases around that. There are two types of tails. One type is ionized gases. Now, I think I mentioned this before. What is it that makes an ion as opposed to an atom? Say again?
I'm not sure.
Okay. Right, that's right. You can tell us all this too because you and Justin were both in the last class. Okay? What makes that up?
Either negative or positive.
Yes, it's got a charge to it. It may be positively charged or negatively charged. It's either gained electrons or lost electrons. That's what makes it an ion. So if it's an ionized gas, it could easily be giving off light. Are there any ionized gases in this classroom?
Fluorescent light.
In the fluorescent tubes. You're absolutely right. Those are ionized gases given there, and they're giving off so much energy they make the phosphorescent material, that white powder that's inside the tubes, gain energy, and then when they lose it, they give off light. So they could be making these tails, or it could be dust reflecting sunlight from it. I guess some give do one, others the other, and they may not know what's doing it. Now here's the interesting thing. The head is always pointed to the sun. The sun is down here somewhere. Okay? Now this comet, is it going toward the sun or going away from the sun? You can't tell. Because if it's going away, it's going to look exactly the same way. The head always faces the sun. The tail is always away from the sun. So this could be coming in or it could be going out. It would look the same way. Because the head is always toward the sun. And the tail is that way. Even if it's going that way, that's what it looks like. So it's rather bizarre. Okay? Tail. What's that? The head is closest to the sun. The tail is always pointing away from the sun. Okay? Now, everybody got this so far? Woo, that's all we have for comments. Okay? And the picture in the book, it looks to be going in another direction. It may not, it may be going the same direction. It's just that the sun is at the opposite side of the picture here. This says it's going near the sun. The tail always points away, whether it's going near or away from the sun. Okay. Now let's move to asteroids. Now, where are asteroids located? Between Mars and Jupiter. Belt between Mars and Jupiter. There it is on the first bullet point here. Now, they can be up to 1,000 kilometers across. That's a pretty good sized rock, wouldn't you say? They have a varied composition. The innermost belt, and by the way, what's the four innermost planets? How do we characterize those? We have a name for them. Four innermost planets are called the terrestrial planets, meaning they're rocky. Okay? The four outermost planets are called the gas giants. Okay? They're giant, huge, and they got lots of gases around them. Okay? Well, it's not surprising then the inner belt of the asteroid belt is called the stony ones, the rocky ones. Okay? The outer belt, they're darker with carbon, and the others scattered among them are mostly iron and nickel. And we'll see later, I've mentioned before already, the vast majority of the Earth's composition is iron and nickel. So that's mostly interior, way interior, way deeper than we'll ever mine. Okay? Now, where were these formed? They were formed from the original solar nebula. And remember, when we were still a protostar, the sun was beginning to heat up enough that fusion occurred, then explosions happened, it blew things out, it did all sorts of stuff. That's probably what formed the planets, and it's probably what formed the asteroid belt. And it's probably what formed the comets and everything else out there too. So, if you look at the diagrams of it and the distances, it looks like there should be another planet in between Mars and Jupiter. Many believe that there should have been one there, but Jupiter was just too big, too massive, and its gravitational force kept the other from forming into a planet. And once it cooled off, there was no hope for it. Okay? So they think Jupiter's at fault for not having another planet in there. It would make sense that you would have one from distances and everything else. Okay? And if you look at this picture, remember Earth 2/3 away between the Sun and Mars. Venus is 7/10 inside the Earth, and Mercury is about 1/3 distance from the Sun to Earth inside there. So there's Mars, and there's Jupiter. Here's the asteroid belt. Doesn't it look like that should be the path of the planet? If you had some other planet in here, that would make sense. But what's going to happen with Jupiter there? So it's just the massive debris floating around. Some really big debris, the largest of which is Ceres, Ceres, and that's actually a dwarf planet. Okay, that came the closest to forming a planet, and it's, I think, on the inside part, further from Jupiter. Now, the scary thing here is that every now and then gravitational nudges hit one of those. And this has been within the last, I think, 10 or 15 years, an asteroid struck the Earth. I believe it was out in Siberia somewhere, where very few people lived, but there was a town nearby that they sensed it, they saw it, they sensed it, they felt the big tremor when it happened. It's crashed into the surface of the planet. Of course, that's in Russia, and they don't let too much out. But and what happened? One of these asteroids must have gotten mixed up in some sort of thing and lost some energy. And once it loses energy, it started falling, and it happened to fall, and Earth just happened to be cutting in its path. Now, that's the type of thing they think happened when, say, Venus was not started spinning the wrong way. That may have been the type of thing that happened when Earth got hit by something. It probably was an asteroid and broke off the moon, okay, from the Earth. So we don't know. Usually asteroids are much more massive than comets. So now we get to the meteors, and that's why I said I really hated they said the three classes are comets, asteroids, and meteorites. No, meteoroids. Because what is a meteoroid? That's the remnant of some comet or asteroid that's just floating around in space. See, most of the comets have paths that they're on. Most of the asteroids have paths that they're on. They sometimes deviate from them or whatever. But when, say, an asteroid collides with something else, like a planet or another object, and we crash out there, okay? Or when a comet comes through, and remember it's a dirty snowball, and as it gets closer to the sun, some of that icy stuff melts, releasing some of the dirty stuff, you know, the rocks and fragments. So those are all left hanging around. They just are out there, okay? That's what a meteoroid is. It's kind of remnants of the other stuff, okay? It just is hanging around in space. It's not really revolving or rotating, it's just hanging around. Now, if one of those meteoroids is hanging right about where the Earth's path is going to go, then it becomes a meteor. If it enters the Earth's atmosphere and starts glowing, because the friction of the Earth's atmosphere is so great, when a meteoroid encounters the Earth's atmosphere, it starts heating up, hot enough to glow. And that's what we see. And we call it two names. Catcher. Never mind, I don't know that song. Falling star. Or shooting stars. When you see just suddenly something streak across the sky at night, way too fast to be an airplane or something like that, it just is, that's a meteor. It's entered the Earth's atmosphere and basically is burning up in the Earth's atmosphere. Okay? Now, there are some times in the calendar year when we actually have what we call meteor showers. They happen so frequently, not super frequently, but you can see a bunch of them in a single night. That's when the Earth passes through what the remnant of the comet's tail. Remember, the comet's tail could be, remember, let's go back here. No, that's asteroid. The comet's tail could be ionized gases. Well, they're not going to form, but dust. Well, what do we mean by dust? Dusty and rocky bits that were just left there. When the frozen stuff melted, getting closer to the sun, it released some of the dusty or rocky bits, and that part makes up the tails. Well, the comet kept on going. These were left over, okay? And when they were left over, and the Earth passes through that, where the comet's tail was, we hit them. Okay, we actually run into them. They don't run into us. We run into them, and there are certain times of the year where we hit different comet's tails. Okay, we'll go to that in just a minute. Okay, now it's a meteor once it comes into the atmosphere and starts burning. Most of the time, they burn up completely. If it's just little pieces of dust or rock, they burn up completely. But if they're big enough to start with, then they burn, but if one of them makes it to the surface, that's when it's called a meteorite. So that's why I disagreed with them calling them comets, asteroids, and meteorites. That's only meteorites when they hit the Earth's surface. They're meteoroids when they're just out there floating around, whether they're in the path of the Earth or not. Those are meteoroids. Okay? So then let's look at the meteorites. What are they made up of? This is meteoroids surviving the trip through the atmosphere when it's heating up and burning and actually strikes the Earth's surface. Again, there's three types of these. Those that are mostly iron, those that are stony, and actually there's two subtypes of that, chondrites and achondrites. And really what a chondrite is, it's made up of little spherical structures. Achondrites are not made out of spherical structures. Okay, now that sounds rather strange, doesn't it? Does anyone know what slag is? Okay, you lived here in the Birmingham, Bessemer area most of your lives, I'm guessing, and all these coal, steel mills and stuff like this. Say again? Yeah, look at you. What's that? Okay, and how would you characterize that stuff? And isn't it sort of beady? Yeah, it's like little balls. Because when something heats up really quickly and cools quickly, it's usually going to be in a sphere shape, spherical shape. Because the smallest surface area for a hot thing to have is a sphere. Okay? So yeah, that's what it is. So think of slag. These have been things that have been heated very hot and then cooled into these things. Those are the chondrites. Those things that are irregular and not spherical, those are the achondrites, not spherical. So you have iron or stony, and the stony could either be chondrites or achondrites, or you have a mixture of the two, stony iron. Okay, so that's what most of those meteorites will be. Now, where I grew up in Georgia, on a farm in Georgia, we used to find especially along a creek, but in some of the fields too, we'd find these really odd-shaped pieces of very dark and heavy material. It really looked like iron, and it probably was. Now, some people describe that as bog iron, which maybe it was, because it was usually near creeks and things, but others swore that that was probably some of those iron meteor residue, okay? That maybe some pretty large iron meteorite hit the Earth, maybe broke into many pieces, or maybe several of them fell at different times, and we have several pieces. I don't think I have any here in Birmingham, or at our house here. I should bring some over from the farm, but I don't know for sure that's what they are. But some people suggest that's what they were. Now, here are when we have those meteor showers. Okay? And each of these is because at any time of the year we're at some position around the sun, right? And at different times of the year, if the last comet went out that way, whenever we get around here, that's when we're going to have the meteor showers from that residue from the comet. This one's called quadratid. That's the basically the constellation in which you'll see the meteors, most of them congregate. And that was January 3rd. Not going to happen this term, okay? And that you see about one meteor every 2 minutes, approximately, okay? If it's a clear night and the moon's not too bright, okay? Clear dark nights, you'd see about one every 2 minutes, okay? The equid, that's in Aquarius, May 4th, you're only going to see about one every 12 minutes, okay? 5 an hour. Perseid, that's in Perseus, that's one about every minute and a half, okay? And that's August 12th. We'll see that, well, right at the end of the term, after the end of the term. Go out on a clear, dark night. Hopefully August 12th will be that. Sit out there, and if you sit there long enough, now you probably need to get out in the country, because in the city you have light pollution, right? So you can't see it in the city. Get out in the country somewhere, okay? Drive out somewhere and find a good, safe place to park and look at the night sky. If it's a clear, dark night around August 12th, better on August 12th, you'll see about once every minute and a half, you'll see meteors, possible. Orion is my favorite constellation. It's easiest to find. It's going to be in October, only about once every 4 minutes. Taurus, remember Taurus the bull, okay? Twice in November, one, as we passed through where it came in and where it went out again, once on the 1st and once on the 16th. Only one every 12 minutes or so, so you're probably not going to have the patience for that. Or one in Leo on November the 17th. But then, Gemini, if you can find Gemini out there on December 12th, it's the day before my wife's birthday, okay, you do that almost 1 a minute, okay, almost 1 a minute. Now, it's getting pretty chilly by then, so you may want to stay out there too long. Bundle up real good, and you'll see these meteor showers. All right, I think we beat, well, we didn't quite. We need pictures of these, and we really don't have time. This is where we'll pick up for next time. Look at your book, okay? That meteor table is on page 395. The next things we're going to look at, they're not quite the same pictures, but they're close. And this is on page 359. So that's where we'll begin next time. Okay. What's that? Okay, not Thursday. Thursday, that's what I was going to say next. If you'll notice, we're real close to the end of the chapter. We'll fit. Second? Lab will be Thursday. We'll finish this chapter in the first hour, easily in the first hour. We'll probably get started on chapter 16, okay? But then when we get to 1:30, so we'll go for this for an hour and a half. When we get to 1:30, so we'll give you 2 hours for lab, we'll start the next lab, okay? And then the test will not be until next Tuesday, last 30 minutes, okay? Good deal. Appreciate your being here. Thanks for hanging in with me. And Titus didn't show up. I didn't show up. Kayla didn't show up. And Adam didn't show up. Yes, ma'am.
When do you put in attendance?
I'm sorry.
When do you put in attendance for us?
When do I do what?
Put in attendance for us.
Usually after this next class I do.
Okay.
Right.
Cool. I was wondering because the Pels that were supposed to come out today,
Right.
Miss Williams called me this morning because I didn't have one and I'm supposed to. And she said that it was because after they put me in your class, it was after the deadline.
Okay.
So she told me to check with you and make sure that you had my attendance.
Absolutely. You've been in there, but you see they cut the checks. You see you didn't enter the class until After that, see,
Second week.
I put in the attendance that Thursday afternoon. Okay, it may have been Friday morning, but I believe it was Thursday afternoon. You came the next Tuesday. They made the first check cut either Friday or Monday,
Right.
and you missed that one. So you should make the next one because I put in this attendance after that class and so
Right.
I go to
Awesome.
the next class. I have 30 minutes after that class. I usually try to put attendance.
Cool.
on
I
that.
just wanted to make sure that you did have fun because she told me to ask. So awesome.
Yeah.
So I'm good.
So whenever they cut the next batch of checks, you should have it.
Thank
You just have to ask them when that is.
Yes, sir. Thank you.
Uh-huh.
I just want to let you know, like, if you see me doze off,
I
I just want to let you know, like, if you see me doze off, I'm not trying to be rude
Oh,
or anything, because, like, I work nights
Yeah.
and then I go to school in the day.
And I'm
So,
Mr. Sandman.
Yeah, I know that, like, sometimes, like, there's other professors that, like, get, like, really upset and, like, get, like, really mad at me and, like, call me out and everything, but I was just wanting to let you know I'm not trying to be rude.
I
I've
never
probably
suspected
only
that.
had, like, 2 or 3 hours of sleep.
Right. I'm so
So then I
sorry.
come here and I'm just like, I'm really trying to listen and
Yeah.
everything, and I'm like,
My wife says, if I ever can't sleep, I just ask you a question, and you start droning on, I fall right off to sleep. So I'm used
oh
to
no,
it. That's
it's not
okay.
even
I know.
It's like, I just,
Yeah, I know.
yeah.
Yeah, I'm amazed that you can stay awake as much as you do with only 2 or 3 hours sleep. I couldn't. So
Yeah,
congratulations.
Like, I'll doze off and then I'll wake up, and like earlier I dozed off and I was like, oh god, how long have I been asleep? And we were still talking about Jupiter, and I was like, okay, not that long.
Yeah.
I was like, I fell asleep talking about Jupiter, and he's still talking about Jupiter.
Yeah.
So I haven't missed that much.
Yeah, good deal. Don't worry, I don't get offended at all.